Hi everyone, my name is Travis, and I'll be telling you about joint work with my collaborators Nina Balcan and Wesley Pegden on semi-bandit optimization. This paper is about new algorithms for online piecewise Lipschitz optimization, and our algorithms are the first to take advantage of semi-bandit feedback, which in our settings allows them to simultaneously be very efficient and have no regret. Our motivation for studying this problem comes from the field of data-driven algorithm design, where the goal is to use data to design algorithms for specific application domains. In the online version of this problem, we start with an algorithm that has configurable parameters, and we encounter a sequence of problem instances coming from some specific application domain. We choose algorithm parameters for each instance as they arrive, and our goal is to perform nearly as well as the best parameters in hindsight. Prior work on data-driven algorithm design shows that for many parametric algorithm families, the utility we care about optimizing is a piecewise Lipschitz function of the algorithm parameters. Roughly, this means that the utility is well behaved in large portions of the parameter space, but can have jump discontinuities. It's well known that no regret learning is not possible in the worst case for these types of functions, but when they satisfy a natural and mild dispersion condition, prior work shows that sublinear regret is possible. In this work, we design improved algorithms that exploit additional structure in data-driven algorithm design problems that gives rise to efficiently computable semi-bandit feedback, and we'll talk about how that improves the algorithms in a little bit. To make things concrete, let's talk about one parameterized algorithm family that we apply our results to in the paper. It's a greedy algorithm for the knapsack problem, and to remind you, in an instance of the knapsack problem, we have n items, each with a size and a value, and a knapsack with capacity k. Our goal is to choose the subset of items of highest value that fits into the knapsack. This is a classic hard problem, so you might resort to using a greedy algorithm like the following one. This algorithm has a single parameter rho, and it assigns a score to each item, which is just its value divided by its size raised to the power rho. Then, in decreasing order of score, the algorithm adds each item to the knapsack if it fits. Changing the value of rho changes the order the algorithm considers the items in, and ultimately the value that we get. So for this type of algorithm, our goal is to find the value of the parameter rho that gives the highest value on some specific source of knapsack problems. Just to make the connection to piecewise Lipschitz optimization, it's not too hard to see that for this algorithm family, the value that we obtain is a piecewise constant function of the algorithm parameter. The key idea is that as we vary rho, the relative order of any pair of items changes only once, and therefore there are at most n squared places where the item ordering can change, and between those n squared parameter values, the algorithm output is constant. Okay, so next I'd like to be a little bit more formal about the learning protocol that we study. So we imagine a game between the learner and an adversary that takes place over t rounds. On each round, the learner chooses a parameter from a d-dimensional parameter set C. The adversary chooses a piecewise Lipschitz loss function mapping parameters to losses. The learner suffers the loss of the parameters that they chose, and then they receive some feedback about the loss function, which I'll come back to in a second. In these types of problems, the goal of the learner is to minimize their regret, which is the difference in their cumulative loss compared to the best fixed parameter in hindsight. So for the feedback, there are a couple of different well-studied feedback regimes. The first and easiest case is full information feedback, where the learner observes the entire loss function, which means that they know the loss of every parameter vector that they could have chosen. On the other extreme, under bandit feedback, the learner only observes the loss of the single parameter vector that they chose. And finally, in this work, we're going to focus on an intermediate feedback regime called semi-bandit feedback, where the learner observes the loss for a subset of the parameter space. So it's worth emphasizing that in the context of data-driven algorithm design, the difference between these different feedback types is mostly in terms of computational cost. So evaluating the loss for every parameter to get full information feedback requires many runs of the underlying algorithm and is therefore extremely computationally expensive. On the other hand, bandit feedback requires only a single run of the underlying algorithm, but provides less information to the learner. So what we're going to show is that in many cases, semi-bandit feedback can be obtained nearly as efficiently as bandit feedback, but it gives more information to the learner that enables nearly the same regret bounds as full information. So this is giving a best of both worlds. And just to be a bit more formal about what we mean by semi-bandit feedback, we're going to say that the problem has semi-bandit feedback with m feedback sets if on each round t, there are sets a1 through am that partition the parameter space, so that when the learner plays row t, they learn the loss for all parameters in the same feedback set. And these feedback sets can be different from round to round. Okay, so our main algorithmic result is that we provide an algorithm for semi-bandit piecewise Lipschitz optimization that has the following guarantee. if the adversary chooses loss functions that are piecewise Lipschitz and beta dispersed, I'll say something about that in a second, and on each round there are m feedback sets, then ignoring log terms, the regret of the algorithm is like square root dtm plus t to the 1 minus beta. So d is the dimension, t is the number, the time horizon, m is the number of feedback steps, and beta is a parameter of the dispersion condition that roughly measures the rate that discontinuities appear in small neighborhoods. And so under sort of natural smoothness assumptions, you can usually show that beta is equal to 1/2 for a lot of problems of interest. Okay, so let's compare this to the best known algorithms for the other two feedback regimes, full information and bandit feedback. So the important takeaways are that first, we see that we basically match the full information regret bound, except we have this additional square root m dependence, which is still, dramatically improved over the bandit feedback regret bound. And as we discussed before, the semi-bandit and bandit feedback regimes are both efficiently computable per round, while the full information feedback has a high computational cost. So in some sense, this type of feedback is giving us nearly the best of both worlds. Okay, so let's make this concrete for our knapsack example. And I'll show both how to efficiently compute semi-bandit feedback and also compare the regret bounds we get against the other feedback regimes. So our algorithm for semi-bandit feedback is just a simple post-processing step on the original greedy algorithm. So we start by ordering the items according to the score with parameter row, and then greedily choosing the item subset, just as before. But next, for each pair of adjacent items in this ordering, we compute the subset of parameters that preserve the relative ordering. And for these types of problems, we're guaranteed that these subsets are always given by threshold functions. So for the first pair of items, this order might be preserved on that sort of half ray. The next pair of items might have this subset, and so on. Okay, finally, we output the items that the algorithm selected together with the intersection of these sets that we computed in step 3. And so just for some intuition, all of the parameters in this interval A are guaranteed to order the items in the same way, which means that we'll get the same value when we run the algorithm. And so we've effectively actually learned the loss for all the parameters in that interval. When compared against the full information and bandit feedback algorithms, we see that we match the square root t time dependence of the full information algorithm. We have an additional n term in our regret bound, but we exactly match the running time of the bandit algorithm. Okay, so there are a couple of other interesting results that we didn't have a chance to talk about. First, we also look at linkage-based clustering and provide the first regret bounds for data-driven algorithm design in that setting. We give a simplified definition that's a little bit more intuitive for dispersion. And finally, we give general recipes for applying dispersion-based regret bounds together with some improved analysis tools that lead to tighter bounds than the prior work. Thank you.